Welcome to Mr. Math Academy. Grow your math brain.
Hello friends, welcome back to Mr. Math Academy. So today in this video we solve the numerical. So to find out what is the shear force diagram and the bending moment diagram when the beam is subjected to a point load as well as the uniformly distributed load. Now here the important concept here is, so we just take like first problem is depends on the UDL as well as the point load. In the second problem we will go for the other load here along with the point load like UVL. Similarly we just solve few more numericals here. Now in this problem we have taken only the point load as well as the UDL here. Now in this case he has given a UDL is 20 kilonewton per meter is given, and again the point load is given 40 kilonewton as well as a 20 kilonewton. So for this problem we have to find what is the shear force diagram as well as the bending moment diagram. Okay, now here the concept is very simple. If you just follow the concept like in a previous step, it's like if you just follow the concept here, the problem is very simple, and these problems are very important for the examination point of view. In all the examinations this kind of problems will appear. Now here in this case, so we have taken, this is a given beam element. Now I have written the the load diagram here. So means what, I have just converted the UDL into a point load here. So because once if I converted that UDL into point load, it is easy for me to calculate what is the shear force diagram as well as the bending moment diagram. So for that here, so now at A and B we are having a reactions here because these two are the supports here. So in that particular support we can have the reaction, that is R here at point A. Similarly we are having a reaction at B, so I have taken this is RB. Now this 40 kilonewton which is a point load as well as the 20 kilonewton, that is also a point load here. Now I need to convert this UDL which is of 20 kilonewton per meter for a given length of 2 meter into a point load. Now to convert this, only thing is what, we need to multiply 20 kilonewton to this 2 here, because for 1 meter the load acting is 20 kilonewton but the total length is 2 meter. So it becomes 20 into 2, that is 40 kilonewton will be acting in this particular member here. Now I need to find out again where it is exactly acting. So UDL is always exactly acting at the center. Now I'll just write this 20 into 2 40 kilonewton will be acting exactly half of this length here. Now this is our converted, that is a point load here which is converted from the UDL to UV like a point load here. Now this is 1 meter length, this is 1 meter length. Now this is 2 meter totally, the what he has given. So the remaining here it's a 1 meter. Now this is what we have converted UDL into point load. So after this the problem is very simple. Only thing is, based on this I can calculate what is the shear force diagram as well as the bending moment diagram. Now this is our first step here. Now the second step is I need to find out what are this, okay, what are the reactions over here, like RA I need to find out, what is RB I need to find. To find this, two unknowns are there. So I have to use the equilibrium equations to find this here. We know that the equilibrium equations are like sigma m is equal to 0, and again we can just take the sigma f is equal to 0. Now I'll just calculate what is RA and RB. So I'll consider that is a sigma m is equal to 0. Now this is a moment, that is the summation of the moment will be equal to 0. Now where we have to take, so because I need to consider any one of the reference point here, I can take any of the reference point like A is there, D, B and C. Out of this we can take any one of the reference point. By using that reference point, with respect to that reference point I can have to calculate what is the bending moment and I need to equate it to 0. Okay, but in this case, so where the reactions are there, because here also one unknown is there like reaction A, here also unknown is there. So that for that purpose I'll consider this A as my reference point, so easily I can get the value of RB here instead of taking the D and C or other any point here. Now I'll consider sigma m is equal to 0 at point A, and sign convention is also very important here. So I'll just take the clockwise movement is positive. Now with respect to A, if the movement is acting like a clockwise, so I'll have to consider that will be a positive here. Now we just see here moment is nothing but it's a force into distance here. Now this 40 kilonewton is acting downward here. So which means, so with respect to this A, 40 kilonewton is acting downward. So it means what? It is rotating with respect to A here. So now the moment becomes 40 into this distance I have to consider. Similarly, so 40, this point load is also acting downward. So means what? It rotates in a clockwise direction with respect to this A. So that is nothing but it's a positive, because the sign convention what I have taken is clockwise positive. But total distance I have to take 2 meter, because we are taking A as a reference point. Now the reaction at B, that is also a force here. So but it is acting upward, means with respect to A, this will be acting counterclockwise direction, which is opposite to my sign convention. So I have to take this as a negative, but the total distance is 4 meter. Similarly, we can go for the last one, which is a clockwise rotation with respect to A. So that will be a positive. Now I will just write the value over here. So that gives 40 into 1 meter, that is a plus. Again the second point load, that is 40 into 2. 2 is nothing but total distance here. And the third one is reaction at B, and the distance is 4. I have taken minus because of the counterclockwise rotation with respect to A. The last one, 20 into 5, that is the total distance, and equal to 0. Now we just simplify this so that easily I can get the value of a reaction over here. So this is 40, so this is 80, so 4 RB is there, and this gives the 100 is equal to 0. Now this is 120 and 100 is 220, so this is minus 4B here, 4 RB, that is equal to 0. Now we just take this term to the right hand side, so I can get 4 RB is equal to 220 here. So from this I can get RB is equal to 55 kilonewton. So this is my reaction at B, what we have calculated. So directly I will write the value of this here, 55 kilonewton. Now again one more reaction is there, area. I need to find out this. So I will use one more equilibrium equation. So that is sigma F is equal to 0. I can use the x axis in the y axis both the direction, but depends on the problem here. But for this problem I will use the sigma F is equal to 0, but only in the vertical direction I will consider here. Now if the load is acting upward, I will take the positive, because this is the sign convention what I have to consider. That is the second equilibrium equation. Now this is acting upward, I take the positive. 40 is acting downward, take the negative, because of with respect to the sign convention. Here we are taking only the forces here, we are not considering the moment, because when we are considering the moment we have to multiply that force into distance here along with the sign convention. Now this is plus RA minus 40 plus reaction is acting upward B, 55 and minus 20 here. So which gives RA, so minus 40, so the next one is minus 40, the reaction is acting 55 upward direction, I will take the positive, the last one is minus 20, which is equal to 0. Now we just simplify, this is minus 80 and this is minus 220 is minus 100, so plus 55, which gives RA minus 45 is equal to 0. So again, so that I can get RA is equal to 45 kilonewton. So this is my reaction, 45 kilonewton. So now the second step is over. Now after this the problem will become simple. So this is the thing what we have to remember, and it's a important here. So after this, based on the same thing, we can easily calculate what is the shear force diagram and the bending moment diagram. Now we have to find out the shear force for this beam element. So to calculate the shear force here, so shear force diagram, so I have represented with the V here like a shear force for that. Now I need to find out the shear force at every point like A, D, B and C, which is given in the beam element, by considering the both left side as well as the right side here. Okay. Now to calculate this, only we have to consider the forces. After that again I need to go for some sign convention here. The very important thing is sign convention. Now if I write like this, so that is the section here. Section means that is the reference point like A, D, B or C. This line indicates like point A, D, B and C. Now with respect to this point A, either it may be any of this point, if the load, this is your load here, for example, if I take, if the load is acting upward direction on the left of this reference point like A, okay. Similarly, if the load is acting downward direction with respect to this reference point, any of the reference point, so I will consider this is a positive shear. If it is acting opposite to that, we will just take the negative. We will just see how it works here. Now again, with respect to A, on both the side I have to calculate the shear force like left of A as well as the right of A. On the left hand side we do not have any forces, but on this particular point A the load is acting, but we should not consider the load which is acting only on that particular point, because the left of reference point means we have to see the left hand side, the right of A means we have to go back to that one right hand side. If it is load is acting on that particular point, it is nowhere related to the left or right, okay, it is on that particular point. So that is why I will not consider the load which is acting on that particular point to calculate the shear force. Okay. Now I will consider the shear force at A, left hand side, shear force at A, right hand side, that is nothing but right of A. Now the next point is D is there, shear force at D on the left hand side, shear force at D on the right hand side, means we have to go in a continuation like A, D, B, C similarly. So B is there, left hand side, B right hand side, C left, C right. The first and the last one is 0 because there is no force with respect to A on the left hand side. Similarly, there is no force on the point C on the right hand side. So I will consider it will be a 0. Now after this I need to find out the shear force at A on the right hand side. Now we just see here, these are the forces which are acting on the right of A. Now this is are acting downward here, this is upward and that is downward, but we have to see the sign convention here. Now this is the reference point A now, that center line. Now if the load is acting downward, we should have to consider positive. Means what? So 40 is acting downward, positive I will take, this is also positive, minus 55 and plus 20. So because according to this sign convention, but I will not consider the 45 which is acting on that particular point. So this becomes 40 minus 55 and again the last one is 20, which gives, this is 100 and minus 45 which gives, it is a 45 kilonewton. Now that part is over. Now we will go for the point D. Again we have to calculate by left as well as the right. With respect to D, we are having two forces on the left hand side like 45 kilonewton as well as the 40, but I will not consider the load which is acting on that particular point, that is 40 kilonewton. Now when we are taking the left of that particular point C, we have to see only the left of this one, that is the force of this one. We do not have to consider this now because this center line is our reference point. Now for this center line indicates the point D. Now we are calculating the left of C means, left of D means, so I will just consider this sign convention. If the load is acting upward, I will take the positive. Now this is positive because with respect to D, upward positive, this is minus 40, this is plus 45 and this is minus 40, which gives 5 kilonewton. Now, so we are calculating the right side of D. So this is point D and we are calculating the right hand side. So this is 55 is acting upward, this is 20 acting downward. But we have to consider the sign convention means this is the reference line. Now right hand side, if the load is acting downward, we have to consider that is a positive. So this is minus 55 and that is a plus 20. This is minus 55 and plus 20 which gives minus 35 kilonewton. Now we have to find out the next one is the shear force at B on the left hand side. So left hand side means we have to consider these three forces. Again we should not consider the load which is acting on that particular point B here. So this is acting upward. When we are seeing the when we are calculating the left hand side, we have to see the left hand side figure here. Upward positive means 45 is acting positive. This is minus 40. This is also minus 40. So this is plus 45 minus 40 minus 45. Sorry, minus 40 again it gives minus 35 kilonewton. Now right hand side of B, so only there is a one force is acting 20. Now we have to see this figure downward, we have to take positive. So means what? I'll get the value only 20. Now again C, on the left of C, all these three forces means four forces also we have to consider, but apart from the 20 kN we should not consider that one. This is 45. So left means you have to see this figure, upward positive means this is 45 positive, minus 40 minus 40, and this is plus 55. So 45 plus minus 40 minus 40 plus 55, which gives this is 100 and again 20 kilonewton. So these are the values what we are getting here. Now all this what the value we are getting here, we just write in the like a sketch here, like a diagram here, that gives the shear force diagram. Now this line indicates it's a reference line, like a reference line means it's a zero line here. In x axis indicates it's a length here, x in terms of meter. The y axis indicates it's a shear force in kilonewton. Now at point A, shear force is 0 and 45. Now this is the shear force is 0 here, 45 means somewhere here I will consider. So if I take this is 45 kilonewton. Again at D, 5 kilonewton minus 35. This is point D, this is A, this is my point B, this is C. At point D, so 5 is there, so somewhere here, and again it comes to the minus 45, minus 35, this is minus 35 if I take, minus 35 kilonewton, this is plus 5. Okay, again minus 35 plus 20, so minus 35 is same on the same line, straight line, but we have to take it on the point B. Again it goes to the 20 on this side, that is the axis. The positive value we have to take above that particular line, the negative value means we have to take on the downward. The last one is the plus 20 is there, that is at point C, again it will reach us to the 0. So this is 20, then it comes to the 0, means what? I have to draw a line like this, that is 0 to 45 at A, 45 to 5 kilonewton at D, again it will goes to the minus 35, continuation we have to follow. Then it will follow the same minus 35 on B, again minus 35 to plus 20 on the same point B, again plus 20 to plus 20 on point C, again it reaches to the 0. Now this is what our shear force diagram. Now here all the we have to draw a straight line curve here. Once if the UDL is given and the point load is given, means we have to draw a straight line for the shear force diagram. But in case of bending moment diagram, that is a different part here, because we have to draw some like a curve, parabolic curve for a different sections here. Now this is what our shear force diagram. Now we'll go for the what is the bending moment diagram. Next we'll go for the what is the bending moment here, like a bending moment diagram. Now the bending moment diagram is only we have to find out at reference point like A, D, B and C. Now we no need to calculate left and right for all the points here. So that also we have to find out in some like some special cases here. So that directly will I will find out the bending moment at A, bending moment at D, bending moment at B and bending moment at C. Now very important thing is the bending moment, so we have to take either left or either right. So for that also we will be having some sign conventions is there. So now this is my reference line if I take like point A, D, B and C. Now if this is our beam here, the beam which is given, if the beam bend like this on the left hand side because of the applied load by considering the moment here, if the beam bend like this on the left of this reference point, again on the right hand side if the beam bend like this because of the applied load in any direction, depends. Okay, now this is the bending because of the applied load like this. So because of that we have calculated the moment now, which gives the positive bending moment here. Now this is called as a sagging moment. So we have to consider this is a positive here. If it is in the opposite direction, we should take the negative. This somewhat indicates like a smiling face, just to remember here, the smiling face, it indicates what? It says something like a positiveness. Okay, if the crying face means which is opposite to that, which gives the negative here, just for remember, to remember this. Now always the bending moment at left we have to calculate, or we have to calculate the bending moment on the right hand side. If suppose if I calculate the bending moment, so on the left of A, because there is no force on the left of A, so directly that will be a 0. Similarly the bending moment at C, by considering the right hand side, so there is no force on the right hand side of C, that is also a 0. Means what? At the extreme positions of a beam, I can take the bending moment will be 0 here. For this problem, the bending moment is 0 at A and C. Now I need to find out the bending moment at D and bending moment at B. So to calculate this, we have to just see again, I just see this one. So with respect to this, I will calculate what is the bending moment at D. Now important thing is, either we have to consider the left of the particular point D or right of that particular point D. You can take any one. Now I will consider the left hand side, and again we should not consider the load which is acting on that particular point, because the force into distance, because the distance is 0, because which is okay like following on the same line, okay, that will be a 0. So which is not come into picture here, only these two forces will be considered. Now this load is acting upward like reaction. Now this is the reference point we are calculating here, that is a bending moment at D. Now because of this load, this part of the beam bend like this, okay, for easy to understand here. So means what? If I just compare with this figure, sine convention, the center line indicates my like a reference point D. Now we are calculating the left, by considering the left hand side means I have to see this figure, so which is similar to this. So I have to take, that will be the positive here. Now this becomes 45 into total distance we have to consider from the point D. So now this is positive. Again there is one more load is there, 40 kilonewton, but because of this 40 kilonewton, this part of beam will try to bend like this. So now if I just compare with this one, so which is opposite to my given reference here, the sine convention, which means we have to take the negative here. That gives, this is 40 and distance is 1. So which gives, this is 90 and this is minus 40. I can get 50 kilonewton meter, that is a moment. Now bending moment at B. So we can calculate by considering the left of the B here or right of the B. If I take the left hand side, there are three forces are there, 45, 50, 40 and 40. Instead of that, if I consider only on the right hand side, only one load is acting, easily I can calculate. And again 20 kilonewton is acting downward, because of this 20 kilonewton, this part of the beam will bend like this. So now we have to see this reference here, this is the point C now, sorry B. With respect to B, we are calculating the bending moment by considering the right hand side force. So right hand side force means I have to see this figure, so which is acting downward here, but here the upward we have to take the positive. Now which is opposite to that means, so it will be a negative, which gives 20 into 1, that is the distance, and it is a negative 1. So which gives, it is a minus 20 kilonewton meter. Now whatever the values what we are getting here, we just write in the scale, which gives the bending moment diagram for this one. So this is the line here. Now this is point A, this is point D, and this is my point, okay, like a B. So this is a C. Now at A the bending moment is 0, it will be somewhere here. Now at point D the bending moment is 50, so I will just consider somewhere here, which gives 50 kilonewton meter bending moment. At point B the bending moment is minus 20, if I take this is a minus 20 kilonewton meter. Now finally at point C it will be a 0. Now the thing is, when we are drawing the bending moment here, so we have to see the given actual problem, that is from A to D we are having a UDL means, but when we are drawing the bending moment, wherever the UDL is there, so we have to draw the parabolic curve. but in the shear force diagram only some inclined straight line we have to draw. So now here to here I just draw a parabolic curve because of the UDL here, only in the bending moment diagram. Now after that, some D to B directly it's a point load is there, so I just draw a straight line. So again here also point load is there, I'll draw a straight line here. Now this is what our bending moment diagram. So this is actually the given in the problem, and one more concept is there. So in between this D to B, I'll just take the point Z here, where the bending moment will becomes 0 here. So that point is called as a point of Contra flexure. I take this as point of Contra flexure. Now point of Contra flexure means where the point like a bending moment will become 0 in between the beam, that point is called as a point of Contra flexure here. So easily we can identify what is the distance of this D to Z, where the bending moment becomes 0. We just here this is a 2 meter means it is somewhat the more than half of this here. So it is the value, the distance from the D is more than our 1 point here, that is a 1 meter. So easily we can mention easily we can assume that will be the where the point like bending moment is 0 here. We can consider like it may be 1 point or something here, but we can calculate by method like by the geometry here, that is to find the location of point of Contra flexure. So now I'll consider this like similar triangles here. So it will be like this. Now this is point D is there. So somewhere here the 50 kilonewton is acting. I'll consider only the magnitude. So this is 20 here. This is point Z and this is point B. I need to find out this distance. That is nothing but at which distance the bending moment becomes 0. Now I'll consider if I take this is my X here. That is the distance that I need to find out. But we know the total distance from D to B, it's a 2 meter. Now the upside this length becomes it's a 2 minus X, that is the total distance minus this one. Now I have to find out this what is the X here. Now if we just see these two triangles, these are the similar triangles here. Now by the geometry I can take the relation like adjacent by the height, that is opposite. Similarly for the second triangle, that is adjacent is this one. So this is adjacent and by height. So for this 2 minus X by height I'll consider. So which gives 2x minus by 50. So sorry, this is 20. Now we just cross multiply here. So it's a 20x minus is equal to 100 minus 50x. Now we just take this term to the left hand side, it becomes 70x is equal to 100. Now we can get the value here, x is equal to 100 by 70. So which gives 1.43 meter. Now at a distance of 1.43 meter from the point D, I can have a bending moment will be 0 here. This is 1.43 meter. That is my point of Contra flexure. If you like this video, please comment, share it to your friends and subscribe to our channel.